Okay, so in this problem, number 22, it's similar to 18 in that the energy is being transferred from one object to another. So you have, in this problem, you've got a hammer. The hammer is going to come down and hit the lever. When this hits the lever, that's going to send the metal piece up to hit the bell. And the reason why it's hard to do is, like if you went to a carnival and they had this, it's not easy to hit the bell. I mean, you really have to swing very fast in order to make this ring the bell. Most people, it's just going to go a little bit up and come back down. And the reason for that is they damp the lever. So a lot of the energy is absorbed by the lever, and very little of it is transferred to the metal piece. In this example, they're saying 25% of it's being transferred to the metal piece. Now, my equation is going to be for the metal piece. Now, this is going to go up, and it says, how fast must the hammer be moving when it strikes the lever so that the bell just barely rings? So we pretty much want this to go up and run out of speed right when it gets to the bell. So the final position will be, we want the velocity to have been lost when it gets there. It also says that there's friction on the way up. So I have work that's negatively impacting this, that's slowing it down. So I have to overcome that. So I'm going to write my conservation of energy equation for this metal piece as it goes up. So that's going to be KO plus UO plus, now there are two W's here. There's the work caused by the hammer, and then there's the work caused by friction, and that's a negative work. So I'm going to write that right here. I'm going to take care of the sign right away. That's negative friction, and that's going to equal KF plus UF. So there's my equation. Now, out of those 6 variables, what can I make equal to 0? Because usually something's equal to 0. What can I make equal to 0 here? Now, remember, we're talking right now about the metal piece. It's starting here, and it's going up. So what would be equal to 0? Right, the original kinetic energy is 0 because to begin with, the metal piece is waiting to be hit by the hammer, waiting for the lever to move, so it's not moving. And the final is 0 because it's going to lose, and we want it to just barely hit it. If we want it to hit it hard, then we would want it to actually strike with some kind of a velocity, but we want it to get up there and barely hit it, so we want it to have run out of kinetic energy completely. So that's going to be 0 also. What else is 0? UO is 0 because the metal piece is starting at its low point. So there's my equation. That's what's left. And the thing is that the work from the hammer is coming from the work from the hammer is due to the kinetic energy that the hammer has when it makes contact with the lever. So I am going to be replacing the work from the hammer. I'm going to be replacing that with 1/2 m for the hammer, velocity of the hammer squared. But like they said, only 25% of the hammer's kinetic energy is turned into work from the hammer. So, I mean, I can write 25% as a decimal 0.25, or I can write it as a fraction. What is 25% as a fraction? 1/4. So I'm just going to put in front of this 1/4. So now I basically have 1/8 of that. So that's going to be this. Then minus the work due to friction is going to equal the friction value times D. I actually know what the friction value is because it says 10 newtons of friction. So that's the force that's being applied as this thing goes up from here up to there. I know what the force is, the constant force as it's going up, limiting how high this is going to go up. And then on the other side, I'm going to have mgh, but the m here is not the same m as the m over here, because this was the mass of the hammer, this is the mass of the metal piece. So I should probably put another, a variable as a subscript so I can identify the difference between my two masses. And so that's going to be mg times the final height. Now the unknown in the problem was how fast must the hammer be moving, so my unknown is this variable right there. So let's do the rest is just algebra. I know the mass of the hammer, I know the friction, I know the distance, I know the mass of the metal piece, so I know everything other than the velocity of the hammer. So first thing I'm going to do is multiply by the least common denominator. And what is my least common denominator? What would my least common denominator be here? What's 1/4 times 1/2? 1/8. So there's only one fraction, so what's my least common denominator? 8. So I'm going to multiply everything by 8. So when I multiply the first term by 8, I'm just going to be left with mh vh squared. When I multiply the second term by 8, I'm going to get 8fd. And when I multiply the third term by 8, I'm going to get 8 mass of the metal piece, g, hf. So there's my equation. So to get VH by itself, I'm going to move this term to the other side, and then I'm going to divide by the mass of the hammer and take the square root. So doing all that algebra at once, I'm going to have that the velocity of the hammer is going to equal, get rid of this stuff down here, the velocity of the hammer is going to equal 8 mass of the metal piece, G, HF. Now I'm going to move this over there, so since it's minus on this side, it's going to be plus on that side, so it's going to be plus 8FD, and that's all going to be divided by the mass of the hammer. And that would equal VH squared, so it's going to be the square root. So that's what's going to get me. Now, since it was 25%, it was easy to convert 25% into 1/4. But let's say if it was like 31% or 26%. You could put 0.26, so you could write it as 26 over 100. So, for example, let's say if this was 26% instead of 25%, I would have 26 over 100 times a half, so 200 would be my least common denominator. And I could distribute 200 to each one of these, and that way I'm just dealing with numbers and I'm not dealing with any decimal numbers. So the next step is to, some of the solution is here. So now we just plug in the numbers. So the velocity of the hammer is going to equal the square root. A lot of things to plug in, so I'm going to make this long. 8 mass of the metal piece, gravity times h, plus 8 fd, all divided by the mass of the hammer. So the mass of the metal piece was 0.4 kilograms. So that's going to go right here. Gravity is 9.8 meters per second squared. The height, it's going 5 meters higher than it was, so that's 5 meters. But that's also going to be the distance through which the metal piece is being affected by friction. So that's also going to be 5 meters. And then the friction is 10 newtons. Now I know 10 newtons is a negative, friction is a negative force, but I've already taken care of the sign up here. So I already put it as a negative there. So I don't have to then, if I put a negative there, I basically would be canceling out the negative that I already put. And then the mass of the hammer is 9 kilograms. So this is going to be 9 kilograms. And if you solve this, now when you put this in your calculator, you're going to go that times that times that times that plus that times that times that equals, make sure you hit equals at this point, divided by that equals square root of your answer. If you do all that, you should get 7.87 meters per second. That was the answer for the velocity of the hammer. That's how fast it had to be moving in order to hit the bell, in order to just barely hit the bell. Any questions with that? So let's see. I'll bring this down so you can see most of the solution.